Last time we have considered how to sketch a polynomial function if the function is given to you in a factored form, right? So next, let's have a look at if you are given a polynomial function but in an expanded form like this. How can we convert it to a factored form to find its zeros with orders? Okay, so today let's have a look at common methods you can use to factorize or factor a polynomial. So in this course, we'll introduce the following common methods to factor a polynomial. There are 5 of them. The first one is called factoring out the greatest common factor. And the second one is special expression or using formulas. Then we can also use trial and error or cross multiplication method or factoring by grouping. And last, you can also use factoring by using factor theorem. So we'll introduce them one by one. So the first one is very easy. Factoring out the greatest common factor or GCF. The GCF for a polynomial is the largest monomial that lies in a factor of each term of the polynomial. This process is basically the reverse of the distributive property. So basically that involves 2 steps. The first step is to identify the GCF of the polynomial, right? And step 2 is to divide the GCF out of every term of a polynomial. For example, if you have an expression like this, this is a polynomial in terms of x, right? And apparently 3x minus 1 is a common factor, so we can put it in front. And then what's left in the parentheses is just x plus 5, right? So in this way, we can factorize this to 3x minus 1 times x plus 5. Then if you want to find the zeros, there are 2 zeros. One of them is 1/3, and the other one is -5. Both with order 1, right? Okay, so this is a simple method. If you observe there is a greatest common factor or GCF, you can just factorize that in front of the expression. And the second method is using formulas. So these are the commonly used formulas for factoring a polynomial. So you can have a look at that. And let me know if you need any explanation, okay? For example, a squared minus b squared can be factorized to a plus b times a minus b. And a cubed plus b cubed can be factorized to a plus b times a squared minus ab plus b squared, and so on. And if you have a quadratic polynomial ax squared plus bx plus c, where a is not 0, and you can also always check its discriminant delta, right? If delta is greater than or equal to 0, you can factorize that to a times x minus x1 times x minus x2, where x1 and x2 can be calculated using the binomial formula. By using the quadratic formula, right? Okay. Now let's have a look at example here. Can you factor the following expression completely? Any ideas? Okay, let's have a look at the solution together. So basically there are different methods we can use to factorize that. The first one is we can use the formulas. So note that if we add a 4 here, that's exactly x plus 2 squared, right? But we don't have a plus 4 here, so we need to add a -4 to compensate the plus 4 here. And then copy the rest of the expression. And that gives us x plus 2 squared, right? And then minus 3. Then we can use the formula a squared minus b squared equals a plus b times a minus b, right? And this gives us x plus 2 plus square root 3 times x plus 2 minus square root 3. So this is a factored form of this trinomial, right? Sometimes this is also called completing the square method. And of course, if you don't want this method, you can always use the last method to factorize a quadratic polynomial, right? So first, you can check its discriminant, delta, which equals b squared minus 4ac, which is 12, right? And then we can calculate this to zeros, which is x1 equals this, square root 12, which is negative 4 plus 2 square root 3 over 2. And this gives us negative 2 plus square root 3. And the other 0 is, of course, negative 2 minus square root 3, right? And then this can be factorized to a, where a is 1. So that's just x minus x1, which is plus 2 minus square root 3 times x minus x2, which is x plus 2 plus square root 3, right? You can use either method. Did you get it? Okay. And the third method we can use to factor a polynomial is trial and error method, which is commonly used to factorize a trinomial like this. So if you have a trinomial, for example, x squared plus 5x plus 6, first of all, we can factorize the leading coefficient to 1 by 1 because you basically have 1 here. So 1 equals 1 by 1, right? And then we need to find a way to factorize 6. Of course, there are different number of ways you can factorize that. For example, you can factorize 6 by 1, 6, or negative 1, negative 6, right? And you can also factorize 6 by 2 by 3, or negative 2, negative 3, right? And then in each of the cases, you need to ensure the sum of the cross product will give you exactly the coefficient in the middle, right? For the first case, we have 1 plus 6, which is 7, so this is not the case. For the second case, we have negative 1 minus 6, which is negative 7, again, not the coefficient in the middle. In the third case, we have 2 plus 3, which is 5, which is exactly the case in the middle. So the third case is usable, right? And therefore, this trinomial can be factorized. The first row corresponds to the first factor, which is x, 1x plus 2, which is x plus 2, right? The second row corresponds to the second factor, which is x plus 3. And usually, if you're not very confident with your result, you can always expand it back to check if you will have the same expression, right? If you expand it, you can easily see that's x squared plus 5x plus 6, which is exactly the term, the expression here, right? Did you get it? Okay, and sometimes you will not have a leading coefficient equals 1. For example, you could also have it like a 6 here, right? So in that case, you need to use more time to check different combinations. For example, in this case, different combinations could be either 1 by 6 and negative 12y here can be factorized to either y times negative 12y, or for example 2y times negative 6y, something like that. You need to test different combinations and to ensure that you have a plus xy in the middle, right? And of course, if you have 2x by 3x here, this will give you 6x squared, and 3y times negative 4y here, which will give you negative 12y squared. And then in this case, the multiplication, the cross multiplication will give you negative 8y plus 9, negative 8xy plus 9xy, which is exactly xy in the middle. So this is the factored form of the original expression, which is 2x plus 3y and 3x minus 4y, right? Any questions? Okay, so no, because you are already familiar with this, so let's have a look at some examples directly then. Again, you have a polynomial expression like this. Can you factor the following expression completely? So basically, you have a trinomial, right? So you can try to use cross product method or trial and error method, right? So I'll give you 1 minute to think about this, and then let's have a look at the solution together. All right, let's have a look at the solution together. So if you have a trinomial, you can try the cross product method first, because that's the easiest method, right? Otherwise, if it doesn't work, you can consider other methods. So first of all, we can consider 15, which is factorizable to 3 by 5. And then somehow you need to factorize 7. The only way to factorize 7 is 1 by 7. And in order to have a 38 here in the middle, you have to put a 7 here and 1 here, right? In this way, we will have 3 plus 35, which will give you 38 in the middle. So the original expression can be factorized to 3x squared plus 7, and then 5x squared plus 1, right? And let's verify. If you extend it back, you will have 15x to the power 4 plus 38x squared plus 7. So this is a correct way to factorize the original expression, right? And actually, we can stop here. It's not factorizable further. Okay, any questions? No? All right, then the next method we can use is to factorize by grouping. Sometimes, in some cases, there is a not GCF for all of the terms in the polynomial. Usually, if we have more than 3 terms with no GCF, we can then try factoring by grouping. For example, if we have a expression here, this is a polynomial expression. Well, first of all, we don't have any GCF. But if you group the first 2 terms and then group the last 2 terms, then we can find a GCF in the next step. So in the first 2 terms, there is a GCF x squared, right? So we can put it in front. That equals x squared times x plus 3. Plus, put the common factor 2 in front for the last 2 terms, which we have 2 times x plus 3. So then in the next step, we have x plus 3 is a common factor. Again, put it in front. Then the original expression can be factorized to x plus 3 times x squared plus 2, right? So sometimes try factoring by grouping. That'll give you some GCF. Okay, let's consider another expression here. So this time, if you GCF means greatest common factor. Okay, sometimes if you only group the first 2 terms and last 2 terms, you will not get a GCF in the next step. And you need to test different combinations or different grouping schemes. For example, we can use this x cubed minus 2x squared. Then because we have a minus 4x squared, there is a remaining negative 2x squared. We can group it to a negative 4x here. And then you have a basically plus 4x, right? And we have a plus 6x in the original expression, so there is another 2x which can be grouped with the last coefficient negative 4. So in this way, we will have a greatest common factor negative x minus 2 in the next step. So we can put it in front. Then that equals x minus 2 times x squared minus 2x plus 2. The problem is, can we factorize this expression as well? So basically you can check its delta, right? Delta equals b squared minus 4a times c, which is less than 0. That means there is no zeros for this trinomial or polynomial expression, or quadratic expression. So we cannot factorize this further, right? So this is a final result of the factored form. Okay, now let's give you some examples to check your understanding. Can you factor the following expression completely using what we have learned so far? Alright, let's have a look at the solution together. The first one is relatively easy, right? So we can just group them like this. First two terms grouped together, and then the last two terms are grouped together. So in this way we can put 4x cubed in front, and we'll have we can put a 4x squared in front. Then we have a x minus 2 here. Then in our next step, x minus 2 is a common factor. And note that we can further factorize 4x squared minus 1, right? Which is 2x plus 1 times 2x minus 1, right? How about the second one? Again, if you want to use grouping, factoring by grouping, we cannot just group them like this, because then you will have a negative 2, right? Isolated term. So it doesn't work like this way. So somehow we need to group them such that the ratio between two adjacent coefficients must be equal, right? So for example, we could try add a 3x cubed here. Then we do not have a plus 3x cubed, so you need to add another negative 3x cubed to compensate that. Then copy the rest of the expression. So you have another negative 3x cubed, so that'll be negative 6x cubed, right? Then note that the ratio of the adjacent coefficient to the first two terms is 3/1, right? So to ensure a 3/1 to the next two terms, you need to add a negative 2x squared. So in this way you have a 3/1 ratio, right? And note that in the original expression you have a plus 7x squared, so that'll give us, you need to add a plus 9x squared. Again, to ensure a ratio of 3/1, you need to put a plus 3x. Then you'll have a negative 3x here, so that'll be negative 6x. You must put a negative 6x to ensure there is a negative 3x minus 2. And then negative 6 over negative 2 will also give you 3/1. So in the next step, probably you will have a common factor. For example, we can put 3x cubed in front, then you have a x plus 3 here, minus 2x squared times 3, this should be 1, I guess. So this should be 3x plus 1, right? Then minus 2x squared, you will also have a 3x plus 1 here. Then plus 3x times 3x plus 1. Then minus 2 times 3x plus 1, right? So in the next step, 3x plus 1 is a common factor. We can put it in front. Then we will have 3x cubed minus 2x squared plus 3x minus 2. So note that the ratio of the two adjacent coefficients are 3 to negative 2 now, right? So we can group them like this, first two terms and last two terms, which gives us 3x plus 1 times 2x squared times, 2 is not a common factor, so just the x squared, times 3x minus 2 plus 1 times 3x minus 2, right? So that can be factorized to 3x plus 1 times 3x minus 2 times x squared plus 1, right? Did you get it? Okay, then let's go to the next method. So if none of these methods work, we can go to the next method. So in polynomial function, we have a remainder theorem and factor theorem. So first, remainder theorem states that when a polynomial function px is divided by x minus b, the remainder is pb. And when it's divided by ax minus b, the remainder is p of b over a, where a and b are integers and a is not 0. So this gives us that the fact that when pb is 0, the remainder is 0, right? Indicating x minus b must be a factor of px. And similarly, when p of b over a is 0, the remainder is 0, indicating ax minus b is a factor of px. Or this can be summarized in the factor theorem. xb is a factor of a polynomial px if and only if pb is 0. Similarly, ax minus b is a factor of px if and only if pb over a is 0. Okay, so basically the factor theorem provided us with a way to factorize a polynomial expression, right? Okay, let's see an example here. Use the remainder theorem to find the factor first for the polynomial expression here. 2x cubed plus 3x squared minus 3x minus 2. Then factorize or factor px completely. So note that we need to find a number such that the original expression equals 0, right? If you can find a number b, then x minus b must be a factor of the original polynomial. Or if you can find a fraction a over b, b over a, then ax minus b is a factor of the original polynomial, right? So in this way, you can test the commonly used numbers, for example, plus or negative 1, plus or negative 2, or plus or negative 3. Try putting these numbers into px, and we can observe that number 1 will let the original expression be 0, right? So if you can find p1 equals 0, that means x minus 1 must be a factor of px, right? And therefore, we can use long division to find the other factor of the original expression like this, right? So the other factor is 2x squared plus 5x plus 2. And of course, you can try to factorize 2x squared plus 5x plus 2 using cross multiplication method, which is much easier than the original one because we only have a trinomial here. The highest order is the highest degree. The degree is just 2. So we can use cross product, and we can factorize that further to x plus 2 times 2x plus 1, right? Can you follow me? Then the original expression can be factorized to this. So now the problem is the factor theorem, along with the long division, is useful to factor a polynomial. But how we can find the first simple factor, such as x minus 1 in the previous example, in the first place, right? Drawing blindly from x equals positive or negative 1, 2, 3 might not be an efficient way. Although sometimes it's working, it's not very efficient, right? So the solution is to use another two theorem to help us, which is called integral zero theorem together with rational zero theorem. So let's have a look at this theorem in the next lecture slide. So integral zero theorem states that suppose a polynomial function px has a leading coefficient 1. So we have a leading coefficient 1 here. And the remaining coefficients a minus 1 all the way to a0 are all integers. And x equals b. B is also integer, is the 0 of px. Or in other words, pb equals 0. This is according to the remainder theorem, right? Then we have the following two takeaways. First, b is a factor of the constant term a0. And two, of course, if no pb equals 0, then x minus b is a factor of px, right? So I'll show you an example to illustrate this theorem. A concrete example here. A polynomial function px, consider this function, x squared minus 5x plus 6, has a leading coefficient 1, right? And the remaining coefficients are all integers. And x equals 2 is the 0 of px. We can easily see x equals 2 is the 0 of px, right? In other words, p2 is 0. Then we have the following conclusions. First, 2 must be a factor of the constant term plus 6. And 2, of course, x minus 2 is a factor of px, right? So this provides a way to check the numbers that could possibly let px be 0 in the first place. So this theorem tells us you should test these numbers, which are the factors of plus 6, right? So instead of trying blindly from negative or positive 1 to 3, you should test these numbers first, which are factors of plus 6. So that includes either negative or positive 1, positive or negative 2, positive or negative 3, and positive or negative 6. You should try these numbers first to see whether any number can make the expression be 0, right? Because any number that could make this 0 is a factor of the constant term 6. So you need to try all factors of the constant term 6 first. Okay, so let's see a concrete example here. Factor this expression fully. So suppose we cannot easily see which number will make this expression be 0. Then note that you have a constant, first of all, you have a leading coefficient 1, right? And all other coefficients are integers. And then, according to the integral zero theorem, suppose you want to find a number such that the expression equals 0. Then you should first test all the factors of negative 6, right? So these values include either positive or negative 1, positive or negative 2, positive or negative 3, and positive or negative 6. You should test these numbers first to see if these numbers can make the whole expression be 0, right? For example, if we test x equals 1, substitute x equals 1 to the original x here, you will get a negative 8. Then you can pass positive 1. Then the next number you could test is either negative 1 or positive 2, right? So you can follow either order you like. If you test negative 1, it can be easily seen it's still not 0. So next number you could test x equals 2, right? When x equals 2, p2 equals 0. So bingo, we have found a 0 of that expression, which is x equals 2, right? Then you can again use a long division to find the remaining factor, which is x squared plus 4x plus 3, right? So the original polynomial function of polynomial expression can be factorized to x minus 2 times x plus 1 times x plus 3, right? Did you get it? Okay, so now the problem is if we have a leading coefficient not equal 0, what can we do? We can use the other theorem to help us with that. So let's have a look at the other theorem, which is rational zero theorem. So suppose px equals an times x to the power of n, all the way to a1x plus a0. This is a polynomial function in a more general way, and an is not necessarily 0 in this time. And suppose x equals b over a is a 0 of px. Of course, here a is not 0, and a and b are relatively prime, which means you do not have any common factors. Okay, for example, 2 and 3 are relatively prime, but 4 and 6 is not relatively prime. Okay, and in that way, we have the following conclusions. If pb over a equals 0, then b must be a factor of the constant term a0. Second, a is a factor of the leading coefficient an. And 3, of course, if you have pb over a equals 0, we know ax minus b is a factor of px, right? For example, if we have px equals 3x squared minus 20x plus 12, this is a polynomial function with all the coefficients are integers. And we know that x equals 2 over 3 is a 0 of px, right? And 2 and 3 are relatively prime. Then we have the following conclusions. First, 2 is a factor of the constant term 12. 3 is a factor of the leading coefficient 3. And then, of course, 3x minus 2 is a factor of px, right? So this tells you another way to find possible numbers such that px equals 0, right? If you have a leading coefficient is not 1, then you should test all the possible numbers of b over a, where b is a factor of a0 and a is a factor of the leading coefficient. You get it? You get it? Okay, let's see an example here. Suppose the task is to factor the following expression fully. Vx equals 3x cubed plus 2x squared minus 7x plus 2. So note that we want to find a number such that Vx equals 0, right? So where does the number come from? So note that this time the leading coefficient is not 0, it's not 1, right? So we should test these numbers first, b over a, where b is a factor of 2, a is a factor of the leading coefficient 3, right? So all possible values of b over a are, well, first of all, you need to check what are the possible values for b. So these are either positive or negative 1 or positive or negative 2, right? And what are the possible factors of a? These are either positive or negative 1 and positive or negative 3, right? So all possible values of b over a are these values. It could be either positive or negative 1 and positive or negative 1/3, or positive or negative 2, or positive or negative 2/3, right? These are the only possible numbers of b over a. So you should test these numbers in priority to see if any one of them can make the original expression be 0, right? So you can follow these orders. Testing positive or negative 1, followed by positive or negative 1/3, followed by positive or negative 2, followed by positive or negative 2/3, right? So, for example, when you test x equals 1, you can easily see x equals 1 is actually a 0 of Vx, so you can just stop there, right? And x equals 1 is a factor of Vx. So in order to find this other factor, you could use the original expression divided by x minus 1 using long division. Then the other factor is this, 3x squared plus 5x minus 2, which can be easily further factorized by using cross product, right? So the original expression can be factorized to this. Did you get it? Okay, let's make a practice. Now it's your turn to factor a polynomial by using what we have learned so far, right? although this question is to solve an inequality, but the nature of this problem is to factorize the left side, the function on the left side. If you can factorize that, you can sketch this graph, right? For example, if you can sketch this graph, like this, it can be easily seen the interval effect that makes this polynomial inequality be less than or equal to 0 these intervals, right? So the nature of this problem is, again, to sketch the polynomial function on the left side, right? Can you factorize the polynomial function on the left side? So I'll give you some time to consider that. We will have a look at the solution together, okay? Okay, first let's study the mind behind this question. So sometimes you are given a question that involves the study of polynomial function, right? So that problem could be, for example, this problem, to find a solution for inequality that involves the polynomial function. Sometimes the problem is from the real world, and that involves the study of a corresponding polynomial function. And in order to study a polynomial function, usually we can sketch its graph. If you know the graph of a function, basically you know everything about it, right? So that involves sketching the graph of a corresponding polynomial function. So how we can sketch a graph of a polynomial function? You need to study its end behavior first, right? End behavior, and then study its behavior in the middle. So how do we study its end behavior? You need to study its degree. Find its degree and leading coefficient. That is decides its end behavior, right? That could be 4 different types for end behavior. It could be either this way, or this way, or this way, or this way, right? Depending on the different combination of degree and leading coefficient, right? And in order to study its behavior in the middle, you need to check its zeros with orders, right? How do you check its zeros with orders? You need to factorize or factor the expression. So how do you factorize or factor a polynomial expression? I'll write it here. We have introduced several methods to factorize a polynomial expression, right? Either you can factorize GCF, or using some formulas, or completing the square, or to use cross product. And if none of these works, we can use a Remainder theorem. And the integral zero theorem and rational zero theorem, right? Okay, so back to this question. Of course, we need to simplify that expression first, right? Okay, I'll write it here. Okay, let's simplify this expression first. The original expression is equivalent to, we can either divide both sides using a -2 or +2. For example, if you divide both sides using -2, that gives us x cubed plus 3x squared. minus 6x minus 8 greater than or equal to 0, right? Then we need to study the corresponding polynomial function y equals x cubed plus 3x squared minus 6 minus 8. Of course, if you can factorize that, you will have its behavior in the middle, because we already know its degree. The degree is just 3. Leading coefficient is 1, which is greater than 0. So its end behavior should look like this, right? Then next, we try to factorize that. So suppose we use the remainder theorem together with the integral 0 theorem, because we have a leading coefficient 1, so we can refer to the integral 0 theorem. You need to find a number b such that the whole expression here equals 0, right? So where does the b come from? B is the factor of negative 8. So you need to test b could equals either positive or negative 1, positive or negative 2, positive or negative 4, and positive or negative 8. You need to test these numbers in priority such that y equals 0, right? So let's test. If x equals 1, what is y? Y is just the 1 plus 3 minus 6 minus 8. So as you can see here, this is not 0 but less than 0, right? So when you test the next number, basically intuitively you want the positive side a little larger, so you will have a 0, right? You will have a number that is nearing a 0, but not less than 0, right? So you should not, so probably we should test the 2 next instead of negative 1, right? So let's see, if x is equals 2, we will have y equals 8 plus 12 minus 12 minus 8. So that is exactly 0, right? So that means x minus 2 is a factor of this expression. Right? So how do we find the other factor? We need to use the long division to find the other factor. So I'll write it here. We have x cubed plus 3x squared minus 6x minus 8. So the other factor is obtained by dividing x minus 2. So we can put an x squared here. You will have x cubed minus 2x squared and then the remainder of the first step is 5x squared minus 6x minus 8. Then we will have a 5x here. Then we have a 5x squared. Okay, we do not have a, I have to write negative 8 here. So we have 5x squared minus 10x. So the remainder of the next step is 4x minus 8. So the next step is to add a plus 4. Then you will have a 4x minus 8, and then remainder is 0, right? So the other factor is x squared plus x, 5x plus 4. And therefore we know y equals x minus 2 times x squared plus 5x plus 4, right? And we know we can easily factorize x squared plus 5x plus 4 by using cross product, right? So we can just directly write that to x plus 1 times x plus 4. These are the factorized form of y, right? And then we can sketch its graph. So first of all, we know the end behavior looks like this, extending from the third quadrant to the first quadrant. And so we know there are 3 zeros, which are negative 4, negative 1, and 2, right? All of them with order 1, right? So the function will act like this. First, it will come from negative infinity all the way to the first zero, negative 4. With order 1, that means this function will cross this point and then arrive to its next zero, which also has order 1, which is the odd number, so this function will cross this second zero and then arrive with last zero too. Also with order 1, so the function will cross again, then all the way extends to the positive infinity, right? So this is a sketch of this function. And to this particular question, we do not need the position of y-axis. So you can just leave it there because we want to find any interval such that the function y is greater than or equal to 0, right? So we can easily see that is this interval here from -4 to -1 together with another interval 2 all the way from positive infinity, right? Therefore, we know the solution to star, which is the original solution, is actually the solution of this inequality, which is the interval that x must be between -4 and -1 closed interval, or x is greater than or equal to 2, right? This is your final solution. Wait a second. So the final solution is -4 to -1 and 2 to positive infinity. Okay, here is a nicer writing of the solutions. You can just follow these procedures, right? First simplify, and then study the corresponding polynomial function px. Okay, so if you can factorize px to this, then next we can try to sketch its graph in the middle, right? Like this in steps 3 and 4.